I'm going to start by asking you, do you have any questions? So almost all of you, I think, actually submitted their assignments. And I know some of you had troubles and could not necessarily complete it. It's only like a couple of you who are in this situation. And it's probably due to I don't know, maybe some soldering issues or whatever. But I think we reply to potential questions regarding that. Just maybe telling you to go to office hours or try to schedule a meeting with us to actually debug this. But other than that, do you have any questions?
Yeah, I encountered issues where it was working in the IDE, and then I was compiling it and putting it on the Teensy, and then I was getting no sound, and also not getting when I enabled the serial to print out stuff, I wasn't getting any serial information. And I concluded that it was trying to maybe allocate too much memory, but the Teensy the Arduino interface wasn't telling me, oh, you've allocated too much memory, therefore something is going wrong. It just wasn't telling me that.
Yeah, so thanks for asking that question, David, because it's probably a fairly common issue that some of you are going to encounter using Faust and the Teensy, or actually it's just using the Teensy in general. But basically the Teensy is a very small system, right? And I don't know if you remember what we said right at the beginning of the class, like in week 1 or 2, I don't remember, but the Teensy doesn't have a lot of memory. So it has a little bit of, like flash memory that you can use to put your software or stuff like that, and that memory is big enough usually. But what's missing, what's lacking basically is random access memory. And there is not much that you can do about that basically, other than reducing the size of the memory footprints of your Faust program. So basically, usually when you're gonna try to run a program on the Teensy, and it doesn't make any sound, and the Teensy seems like it's completely frozen. As you said, it's not outputting anything, it's not displaying anything. If there's a serial print or something like that, it probably means that you try to allocate too much memory. And for some reasons, the C++ compiler of the Teensy is not smart enough to tell you if your program is going to allocate too much memory or not. And so basically the only way to know if you're going to allocate too much memory or no is to try the program. And usually a good hint, it's actually fairly easy to guess if it's gonna allocate too much memory or not. And usually in signal processing, what's allocating too much memory is basically anything that needs to store audio. So if you have long delay lines, if you have a reverb, if you have that kind of effects that you found, sometimes they're going to allocate too much memory, because a reverb needs a fair amount of memory because there's a lot of delay lines in a reverb, and it's the same for an echo. So it's kind of hard to exactly say what the limit is, because it's probably going to change slightly from one time to another, depending on what your program contains. But usually I think it will be very hard for you to allocate more than 1 second of sound, basically. So meaning more, any program which is going to try to allocate more than say 45,000 samples, it's probably just not going to run, basically. And
are we ever going to be able to make a sampler that can play back a file?
Okay, so that is a very good question too. So in that case, the answer is yes. You'll be able to do that, but in that case, you're going to have to come up with some kind of hybrid approach between Faust and the Teensy audio library. So the reason for that is because like Faust is in the DSP realm, okay, and to do what you're saying, you're going to need to read audio samples from a potential SD card that you will connect to your Teensy. And you know that your Teensy Audio Shield has an SD card slot reader. So it's actually fairly easy with the Teensy audio library to access WAV files that are on the SD card. But then, like, the smartest thing to do, is to basically use the Teensy audio library to read your samples. And then if you have some DSP to do, you just like do it in Faust, and then you connect your Teensy audio library element, which is reading the audio file, to your Faust object. You basically create multiple objects, and you plug them with patch cords using the Teensy audio library, and then you'll be able to do whatever you want, but basically, because they have to be read from the SD card, like these audio files, that's not necessarily something that Faust is supporting out of the box, because it's basically more Teensy audio library feature than a Faust feature, basically. It's not that Faust cannot do it, but it's just that it makes more sense to do it on the Teensy audio library side. Does that answer your question,
Yeah,
David?
I was thinking that it might involve the foreign functions.
No.
That's not it.
So the foreign functions in Faust are only used if you want to, like, if there is really something that you cannot do in Faust for DSP, like as a block in your DSP chain, then you might want to use the foreign function in Faust. But foreign functions in Faust basically take an input and they have an output. And basically what they do is that they expect that you send like one sample and they give you a sample back, right? And so here it's not necessarily what you want to do, like here you really want to benefit directly from the mechanism of the Teensy audio library. And I think it will be much simpler if you just use the Teensy audio library to read your WAV file in the SD card, and then connect that object that is reading the SD card to a Faust object or to something else, basically. So I know it might sound a little bit complicated like that, but in fact it's actually not that hard, and if you don't really know how to do it, if you go in the Arduino software, there are examples that are specific to the Teensy. Like if you go in File and then Examples, then there are Teensy specific examples, and in the Teensy specific examples there are audio examples. And then if you go in the audio examples, I think there is an example that shows you how to read a WAV file from an SD card, basically, and that's what you want to do, and once again, it's pretty straightforward, yeah.
Cool. Okay, thanks. Yeah.
Sure. Any other questions? It's good that you're asking these questions, because I'm sure a lot of people are wondering the same. So please, there's no stupid question. So go for it. Okay.
Hey, well, here's a dumb question to add. So I'm like looking at the like Teensy picture, and I'm trying to find like the SD card, like how you'd hook up the SD card, like.
No. So
Yeah.
So as I said, the SD card reader is on the Teensy Audio Shield. It's not on the Teensy itself.
Thanks.
Yeah, it's on the Audio Shield. Yeah, it's so there are some Teensys that have a built-in SD card reader, and I think that's the case of the 4.1, not the 4.0. But in our case, if you want to use SD card, you can use it through the Audio Shield, basically. Any other questions or? Cool. So today we're going to talk about OpenScad, which is CAD software, so computer-assisted design software. It's going to be pretty quick because you'll see that it's actually very easy to use, you know, and you know, like the goal of well, one of the goals of Lab 5 is for you to practice OpenScad and try to do things with it. So I'm not going to say too much about OpenScad, you know, because I think it makes more sense for you to actually just you know, practice it. But you know, I just want to give you a very brief introduction of how it works and how we're going to use it in this class. So before I begin, I just want to say that if you are used to another CAD software like SolidWorks, Rhino, AutoCAD, or you know, like, you name it, Blender, you know, whatever, please feel free to use it. You know, I can, and this is why we're only doing one lecture on this. You know, it's because the point of this class is not to teach you how to use, you know, like SolidWorks or complicated CAD software, but I'm sure that most of you actually don't know OpenScad, and you're probably going to find it interesting anyway. You know, like so what I'm saying is that if you want to use another CAD software for your final project, please feel free to do so. You know, like this is just so that people who don't know OpenScad can actually or CAD softwares in general do have a tool to complete their final project, and also Lab 5. Okay, so let me share my screen with you, and okay, there we go. Great. So actually, you know, I'm not going to share this. I'm going to share actually my entire screen because I think it will make more sense. Sorry about that. So share screen, and I'm going to share desktop. Okay, great, cool, perfect. So if you look for OpenScad, there is a very simple website for it. It's openscad.org. And I invite you to all download OpenScad now, basically. It's fairly small, you know, like it's a very, very simple piece of software. So please download OpenScad and install it on your computer. It should work on Linux. It should work on the Mac and on Windows. So it should work for all of you, which is why we're actually using it. Cool. So once you have OpenScad on your computer, the first time you open it, you're going to have this window, and then you just want to create a new OpenScad design. Okay. So OpenScad is a very peculiar CAD software because it actually works with a programming language. And now you're probably like, oh no, another programming language. Well, yes, that's another programming language. But you'll see that there are actually a lot of advantages of using a programming language for doing CAD design. So let me just tell you like what OpenScad is going to allow you to do. So OpenScad is going to allow you to design 3D objects that are ready to be 3D printed in a very, very, very simple way. So in most cases, with less than 20 lines of code, you're going to be able to implement very complex shapes. And so the main goal of OpenScad here is really just to create parts, create objects, right? So in OpenScad, you're not necessarily going to be able to do like assemblies like you would do in SolidWorks or in Rhino, you know, like, so you're not going to be able like to get like a fully assembled prototype like you would in SolidWorks, you know, like which is made out of multiple parts. You know, if you are familiar with SolidWorks, and I know that many of you are because many Stanford classes actually teach SolidWorks. But with SolidWorks, you first create parts like a screw, a case, I don't know, like parts, and then you assemble them together in an assembly, right? So here in OpenScad, you can create assemblies if you want, you know, like, but they're not necessarily going to look good, and it's kind of a pain to create assemblies too, you know, like, so you're only going to be able to create parts, okay? And so once again, if you know SolidWorks, please feel free to use SolidWorks. But you'll see that OpenScad is actually very useful. Okay, so here you have a code editor, and then on the right side you have a 3D screen and like a 3D view, and that 3D view is basically the rendering in 3D of whatever you're going to write on the left-hand side of the editor. Okay. So the most basic thing you can do in OpenScad is to create a cube, okay? So that's what I'm gonna do here. And okay, let me maybe try to zoom in a little bit so that everyone can see what I'm doing. So we're going to create a cube, okay? And to create a cube in OpenScad, you just say that you want a cube, okay? That cube is going to have dimensions, right? And then you need to give it your X, Y, and Z dimensions of your cube. Okay. So in our case, we're going to say that we have a cube whose size is 20 by 20 by 20. Okay. 20 what? So in OpenScad, there is no units. Okay. So basically, the units you give to your objects is the units you decide to give to your object. Okay. So if you decide that your units are inches, then those are inches. Okay. If you decide that units are millimeters, then these units here are millimeters. So in fact, they're going to be millimeters. Why? Because when you export your design from OpenScad to your 3D printer is going to assume that whatever you give to it is actually in millimeters. And we're going to be able to export an STL file from OpenScad, which is the standard format for 3D objects that you give to 3D printers to print something. And your 3D printer is basically going to assume that you are going to use millimeters. Okay. So even though OpenScad doesn't have units per se, we can assume that these units are actually going to be millimeters. Okay. So here you have a bunch of buttons, and this button here is the preview button. So if you click on it, well, you get a preview of your object, and look at this, we already have a cube. And this cube is actually ready to be 3D printed. Okay, so if we actually wanted to 3D print this cube, we could export this to STL. And once again, STL is the format, which is like the standard format for objects that you're going to want to 3D print. Okay, so to export this cube to STL, you're first going to have to render the cube. Okay, so here we just preview the cube. Okay, but in order to generate the corresponding STL file, you're going to have to click on render. Okay, so click on render. It's very quick. Okay, it was just rendered, and then you can click on the STL button here, and then you can save that wherever you want on your computer. And I'm going to call that cube.stl. Okay, I'm going to save it, and now have an STL file which is ready to be 3D printed. Okay, it is really that simple. So some of you probably are wondering at this point, what is the point of having a preview and a render button? Like, why don't you just render every time? So in our case here, we have a very simple design. So it's just a cube, right? But in some cases, you're going to come up with very complex designs. And in that case, rendering your design might take a little bit of time. Sometimes if your design is huge, it's probably going to take a lot of time. Okay. So the point of having the preview button is that whenever you want to see very quickly what your code is doing, you just click on preview. And if you want to generate the final version and get like the final view of your design, then you just click on render. Okay. Do you have any questions so far? Great. So usually when you make something and you want to 3D print it. And it's going to be something that you want to use, you know, like for example, a case or something like that for your final project. Very often, the first thing you're going to have to do to your design is to put holes in it. Okay, and yeah, that's like a very, very common thing to do. So what about we try to put a hole in this cube? Okay, so those of you who are familiar with SolidWorks and Rhino know the paradigm where you basically always start from a 2D object, right? It's like a drawing, and then you turn it into a 3D object by extruding it, you know, or you know, like using other techniques. In OpenScad, the default approach is not that one. Like the default approach is you always start from 3D, okay? And in some cases, we'll see that we can do the same as in SolidWorks, where you start from 2D and then do extrusion to turn it into a 3D object. But it's not necessarily like the easiest approach in OpenScad. So, so basically, the way I'm gonna put a hole through that cube, let me actually make the cube slightly bigger, you know, because I'm gonna say that it's actually 50 by 50 by 15 millimeters. Okay, so now we have a bigger cube. Okay, and so it's a little bit hard to comment on this remotely, you know, like, but you know, usually it's easier to have a mouse with that kind of softwares, you know, than your trackpad, you know, like, but you'll see that if you do like left click, you can actually rotate the object. If you do right click, you can move the space, right? And you can zoom in and out on the object. Okay, I'm sure you'll figure that out pretty easily. Okay, so the way I'm going to drill a hole through that cube is by first creating a cylinder. Okay, and so there is a cylinder object in OpenScad that you can just call like this. It's cylinder. Okay, and our cylinder object, and you see that actually it usually helps you with, gives you some hints with what you can use here. So we can define the height of our cylinder, and we can define its radius and the fact that it's centered or not, okay? So here, what I'm gonna say is that the height of the cylinder, which is h, okay? H is going to be equal to, well, the height of the cube, okay, which is 50, okay? And then the radius is going to be smaller because I want to drill like a small hole throughout the cube, like all the way through. And for that, I'm going to say that the radius is equal to 10, okay? Then I'm going to close this. You don't have to use all the parameters. And then I'm just going to re-render this. And oh, at this, we now have a cylinder. Right. So by default, cylinders and all circular objects are centered on the space. Okay, which is not the case of your cube. You could center your cube. Okay, and if we wanted to center the cube, okay, I'm gonna take a huge risk here because no, okay, there we go. Because I don't remember what the word for this is, you know, like, but we could actually center the cube and say that our cube is center, and this is true. Then I can re-render. Now, look at this. Actually, the cube is centered, but now it's completely centered, meaning that basically it is centered on all axes, you know, like, so the cylinder is actually popping out of the cube. So now I think if we center the cylinder, it's probably gonna disappear because now the cylinder is inside the cube, okay? So if I comment out the cube, you can use comments just like in Faust, okay? And if I re-render it, there is my cylinder. And if I do this, here's the cube, okay? So now what do I do? Well, actually, first, I'm gonna move the cylinder and I'm gonna put it after the cube. And you'll see that there is a reason for that, okay? And now I'm gonna use a command in OpenScad, which is called difference, okay? So I'm going to create the difference of the cube with the cylinder. And for that, I'm going to use the syntax, okay, where I have parentheses here, and I don't put any parameters because there's no parameters for difference, but it's function. So so I do need to put the parentheses, and then I have my curly brackets where I put all these things in here. And then if I run, here we go. You can see that there's sort of a hole through my cube. Okay, and you see that there is a ugly bug, right? So so why is there this ugly bug? Well, the reason why there's this ugly bug is because we only previewed the object, and that's where you see that there are some limitations to actually previewing things. So if you want to see like the final version of this with the hole through the cube, and you want to get rid of the bug that we currently see now, you can actually just click on render, and there we go. So now we have our cube, and there's a hole through the cube. Cool. Do you have any questions? Great. I mean, it's pretty simple, right? So, okay. At this point, before I continue, I want to show you like what happens after that. Okay. So say that I actually want to 3D print this. Like say you want to make like a nice necklace. And you want to put like a rope through that hole that you just created through your cube, and you want to wear it basically, and you want to 3D print it, which you could, because you now all have a 3D printer. So how do you do that? Okay, so currently you can't use your 3D printer because it's probably still in its box unless you already like started assembling it. Why not? But like, what is the next step like to actually send that to the 3D printer? So for 3D printing, and we're going to talk more about that next week when we actually start talking about 3D printing. You can't really just like go from your 3D object, like the 3D object that we have here, to the 3D printer directly, because there are some design decisions that need to be made before the 3D printer can print something. Like 3D printers are fairly plug and play, but there are some parameters that you want to control in order to optimize the way your object is going to be 3D printed. So to do that, you actually need another software. And that software is what we call a slicer, okay? Just like slicing, it's a slicer software. And the slicer software we're going to use for the 3D printers that we have in this class is probably the most common slicer software that people use for 3D printing, and it's called Cura. Okay, so I'm only going to show it to you now, just very briefly. Don't install it because that's actually going to be part of Lab 5. And in Lab 5, you're going to have to assemble your 3D printer, and then you have the instructions to properly install Cura on your system. So don't try to install Cura now because otherwise you might run into issues, because there are many different versions of Cura. And if you just go on the Cura website and try to download like the default version, maybe you're going to run into some issues when you try to use it with your 3D printer. Okay, so I'm just going to show it to you, just so that you sort of get an idea what I'm talking about. Okay, so okay, let me open Cura. So on my computer, sorry, it's kind of a nerd computer, so I need to open it through my terminal. Otherwise, I get some problems. Okay, so Cura is booting. Cura is starting, and once Cura actually is running, it looks like, where is it? There we go. It looks like a 3D printer bed. Okay, so so once Cura will be installed on your system, it will know about the Creality Ender 3 3D printer, which is the 3D printer that you get as part of this class. Okay, So basically, how do I go from OpenScad to the slicer? Well, first, once again, you need to render the object, like so. So just click on render. And once the object is rendered, then you click on STL again, and then I'm going to save my cube.stl again. I overwrite it. Okay. And then all you have to do is to take your STL file that you created. And mine is right here. It's cube.stl. And then you drag and drop it in Cura. And boom, you get your cube with a hole through it. So, like this cube is 50 millimeters by 50 millimeters by 50 millimeters. It is fairly big. Like printing that cube would probably take some time. And some of you are probably like, okay, why don't we use like inches or and not millimeters? Well, it's not because I'm French and in Europe we use millimeters and not inches. It's just that for what we do here, it's more practical to use the metric system, and by default, all these tools actually are in millimeters. So you're just going to have to deal with it, but usually like more and more, even in the US for product design, like people use millimeters or like the metric system, because it is just more convenient and more standard for all the stuff that we're doing here. So just deal with it, basically. Well, I'm sure you can actually configure Cura if you want to like configure it in inches, but I think it's a good practice to know about the metric system. Anyway, so that's it, and then you can use the default parameters of the printer, and I'm not going to comment that more at this point, because it's not the goal of this class, but you can just click on slice. Then you put whatever will be produced on an SD card that you put in your 3D printer, and you can print the object. It's really just that simple. So you can see, and that's why like OpenScad is great, that with these 4 lines of code, we actually made an object. Okay, it's a very simple object, but it is an object nonetheless, right? And we managed to export it to our 3D printer software, and the object is actually ready to be 3D printed. Okay. To do all this in SolidWorks or in Rhino without knowing the softwares, it would have taken you probably a week. Because these softwares are way more complicated to use than what we're just doing here. Okay. So still no questions?
I have one question. How do you like slightly offset something from, like say you center it, but you want to move it like a little bit up or down?
Great. Okay, so that is a very good question. So I was actually gonna get to this, but before I answer your question, I just want to point you on the OpenScad website to the most useful resource in OpenScad, which is the cheat sheet. Okay, so you just click on this, okay, or you just look for it on the web, you look for OpenScad cheat sheet. And here you get a sort of an overview of all the functions which are available in OpenScad. They're all here. And you're probably like, that's it? Not more? Well, actually, yes. There are no more functions than this in OpenScad. And believe it or not, but with all these functions, you can actually do everything you need to do. Like any sort of shape, you can actually implement it with a combination of these different functions. So the reason why I'm showing you this cheat sheet at this point is because the way to do what you're saying, Hassan, is actually documented in here. So if you look for transformations, the most basic transformation that we can do in OpenScad is a translate. Okay, and you can actually translate an object on the X, Y, and Z axis. Okay, so say for example that we would like to offset our cylinder, which is creating the hole in the cube by a couple of millimeters on the x-axis, for example. Then we would just write translate. Okay, and then we need to put we need to give parameters to translate. Okay, and there are three values, one for X, one for Y, and one for Z. By default, you can just like start by saying 0, 0, 0, you know, and then if you render this again, you know, it doesn't change anything, of course. But now if we want to offset our cylinder by, say, 5 millimeters on the X-axis, we just do this, okay? And then if I render it again, then our hole is now not centered anymore. So, so you can do all sorts of transformations. You can do a translate, but you can also do a rotate, right? So, so for rotate, and you can daisy chain all these functions. You know, it's very easy to use. You know, like so you can just say like rotate, and for rotate, it's the same story. You need three values: one for X, one for Y, and one for Z. And then you need to specify the angle that you're going to use for your rotation. And so say here that I want to rotate our cylinder by 10 degrees on the X-axis, then you just say 10. And it's all in degrees, okay? And then if I render this again, well, you can see that now our cylinder is actually not covering completely it's not really creating a hole completely anymore, you know, because it's tilted, you know, and now like the material of the cube is covering part of the cylinder. However, if we rotate it, yeah, there we go. Now we can see that it's actually the same on the other side. So now if we wanted to still have a hole, you know, like we could easily just increase the height of the cylinder. And we could just like give it a value which is big enough so that it sticks out on the two sides. And because our cylinder is centered, it's going to go on the two sides, right? So, so if I want to add like, say, 5 millimeters on one side of the cylinder and 5 millimeters on the other side, I could just say like 60. It's 5 and 5, right? I just added 10 to the height of the cylinder. And now there is a nice hole going through our cylinder, but it's sort of tilted, okay? Right. So does that answer your question, Hassan, or?
Yes, thank you.
Cool. So actually, you know, like an interesting exercise here. So I don't want to do like too much exercises during the Zoom sessions because I mean, there's not a lot of time every time, you know, like, and there is so much things to say, you know, like that. I think it's better than you do that during labs. But say that, for example, you would want to, let me just get rid of this here. So you want to create an object where there is a hole through that face, but you want a hole through that face, okay? So, so how would you do that? Well, you would create another cylinder, right? And for that, I'm just going to copy and paste this one. Okay. And so now I have two cylinders. Now I can just rotate this cylinder by 90 degrees on the X-axis. Sorry, that was the wrong side. Well, it doesn't matter. It's okay. Like, I mean, you get the point, right? So now I have two holes going through my cube, you know, and yeah, and basically they're on the different faces, right? So now if I wanted to have another hole, you know, like in the other direction, oops, sorry. So that I have like holes on all faces of my rectangle, of my cube, sorry. I would just like copy and paste this, right? And now instead of having a rotation on the X-axis, I will apply a rotation on the Y-axis. There we go. Now I have holes going through all the faces of my rectangle, right? Okay, so something interesting happened here. So I don't know if you noticed, but here I only clicked on preview, and there, like the bug that we had before, like where, it looked like something was covering the hole, even though it was not really covering the hole, is not happening anymore. So why is that? Well, the reason is because I forgot to put the height of my cylinder back to 50. So, if I put 50 again here, then I will get the bug in preview, right? But I will not get the bug if I do the rendering. Okay, you can see that now rendering is taking a little bit more time because the shape is more complex. Okay, so some of you are probably wondering at this point, okay, so why don't we just like try to increase the size of objects that are differentiated so that we don't get the bug, right? Well, you can do it, and it's not going to be a problem. Like it's not going to like change the final product that you get. It's just that it's kind of risky to do it, because in some cases you might mess things up a little bit when you write your code, because you're going to be like, okay, why do I have like this weird value here where there are these 2 extra millimeters? Like so you can do it if you don't want to render things every time. Like put a value which is too big so that you don't get the bug. But then like yeah, it's a little bit risky to do this because you might be wondering like why things are happening this way and not. Okay, cool. Do you have any questions about what we did so far? More questions? Okay, so I don't know how well you can see what I'm doing on my screen, but if you zoom in, you're probably noticing that the resolution of these circles is not very high, right? You can see that there are faces, like our circles are made out of faces, and it's not like a clean circle. So why is that? Well, the reason for that is because OpenScad generates STL files, which are basically a set of Cartesian coordinates in a space. Like, so basically it says, okay, there is a node here, there is a node here, and our X, Y, Z space. But it's not like a vectorial 2D object where, you say, okay, here I have a circle and the diameter of the circle is that, right? When you generate an STL file, in the end, it's just a set of Cartesian coordinates. And because it's a set of Cartesian coordinates, whenever you make a circle, you can only make the circle out of flat surfaces, right? And there is nothing you can do about that. So if you were to 3D print this cube with the current resolution for these circles, you would actually get these flat surfaces. Well, in practice, the 3D printer is maybe not that precise, and in the end, it's probably going to look like a circle anyway. But in some cases, if you use like very precise 3D printers, and the one you actually get in this class is fairly precise, you would probably see these faces. Okay, so how do I solve this problem? So there's a bunch of let me go back to the cheat sheet. There is a bunch of what they call special variables in OpenScad. And these special variables allow you to set global parameters that are going to set like that kind of things, and the thing that I'm talking about here is the number of fragments. So if you want to define the default number of fragments for circular shapes in OpenScad, you're going to have to override this variable, okay? And it's $FN, okay? So here, if I say $FN, and then if I say, for example, 10, which is a very bad value, you'll see why. Then if I render my thing again, you can see that now I have like extremely low resolution circles that are made out of 10 faces. Okay, of course you don't want to use that, like, because now it looks really bad. When you 3D print it, you're definitely going to see the faces now. So on the other hand, like if you say that you want like 100 faces, you render the object. Yeah, that's now that you see that rendering takes time, because it takes time to render all these faces, and then you have to wait. Okay, and now you can see that we have very nice circles. There, we can still see the faces if we zoom in, but now, like if you 3D print it, you will not see the faces. They are too small to actually be properly rendered by the 3D printer. Okay. So some of you are probably wondering at this point, okay, so what is the right value for this? Well, it's really up to you. Like I would say that 100 is like high quality, and in fact, in many cases, you might just want to comment that out when you are working on your prototype. Because it will accelerate the rendering of the object. Once again, like if I render the object here, you see that it's being rendered pretty quickly. If I have this, it will be much slower. So maybe that's something that you just want to add at the very end, like when you're going to 3D print the object, just like add this variable, and then that will be like your final rendering. But when you work on the prototype, you of course don't need you don't need that, right? The preview is not impacted by the time of the rendering with FN. So you can see that if you click on render for 100 fragments, it's actually super fast, right? So so that's another important thing to know in OpenScad. Okay. Cool. So just to finish this tutorial, because there are a bunch of other things that I want to do today, and once again, like the lab is going to be really just about discovering OpenScad. I'm talking about lab 5 here, discovering OpenScad, and just see like what you can do with this software. Because it is a programming language, you benefit from all the advantages of using a programming language, like which are you can create conditions, you can create loops and things like that. So say that, for example, I would like to duplicate this cube multiple times. How would I do this? Okay, so probably the best way to do it first, is to create a function. So in OpenScad, to create a function, you create a module. Okay. And okay, so here's the module, and if you look for the definition of module in the cheat sheet, okay, I don't see it, so you can actually just look for it. Okay, there we go, module. Every time you can actually click on the object to get like the proper documentation of the object, so you can see that the syntax for a module is module name, and then parameters of your module, and then whatever needs to be done. Okay, so I'm going to call this module, and I'm going to call it my cube. Okay, not my tube, my cube. All right, and then for now, I'm not going to put any parameters, and then I'm going to put curly brackets. Okay, and okay, I'm just going to do this nicely. So I'm just doing like proper indentation so that things look good. Okay, so now if I run the program again, there is no more cube. Okay, so if I want to get the cube, I actually need to call my cube now because it is a function, right? So if I call my cube, now I get the cube back. Okay, so here I'm creating a function, a module, and it's my cube, and it doesn't have any parameters. And if I want to render it, if I want to call it, I just call it. Okay. So here you can now create parameters, and so for example, I could create a parameter called hole diameter. Okay. And I can give it a default value, and in our case, the hole's diameter. And in our case, there are actually 10. Oops, sorry. And now I can use this variable in here to configure the diameter of the holes of my cube.
You're missing an R on the top,
Yeah.
by the way.
Sorry, it's just that there's kind of an annoying bug in the editor. Okay, there we go, hole diameter. Great. And so now if I render again, there's an error.
In
because
your
I'm missing
module line.
R
Yeah.
here. Yeah. Great. Okay, so so I still get the hole. Okay. But now I can actually control the size of the hole. And I can just call hole diameter again here, and then I can set it to 5, for example. And now the hole, oops. What did I, holes, sorry. There we go. So now if I render the object, there we go. I get it is a very annoying bug. Like, I don't know if you see it, but the cursor for addition is offset by, you know, like a few millimeters on my screen. So anyway, yeah, there we go. So now I can control the size of the holes on my cube. Okay, so what I was saying initially is you can loop things, you know, like you can create loops to, for example, duplicate things, you know, like, so, you know, if I were a good programmer, I would not have written things this way, but I would have created a loop to create the cylinders, you know, like, but instead here, I'm going to create a for loop. Okay. And so if you want to have like a hint of how for loops are supposed to work, you need to give them a start and an end. And if you go to the sheet, sorry, for loops, okay, where is it? You know, like you can always just look for things by saying for. Okay, there we go. So flow control. So yeah, so basically you can see here that you need to first create a variable and then you give it a start and an end. Okay, so say that here I would like to duplicate my cube 4 times, you know, then I will say that I have I equals 0, you know, and we can see that the syntax is a bit like in MATLAB. And so I'm going to go from 0 to 3. Okay. Then I'm going to put curly brackets. And if I render things, well, I only have 1 cube. And the reason why I only have 1 cube is because I need to translate them now. So I'm going to translate my cube. And what I'm going to do is I'm going to say that yeah, I'm just going to put these default values first. Every time I'm going to want to create a new cube, I'm going to offset it by, say, 60. Okay, so I'm going to say 60 multiplied by I. Okay, now if I render this, here we go. Here are my 4 cubes. So that is the beauty of using a programming language, because if you wanted to do something like this in SolidWorks, it would have taken you much, much more time. You know, like I use SolidWorks a lot, all the time. I love SolidWorks, but really sometimes I just use OpenScad because I want to do something very quickly and it's something simple. It's so much quicker to do it in OpenScad than if I had to do it in SolidWorks. So, or in Rhino or whatever, you know, like, so basically I can now render this, you know, and this is ready to be 3D printed, you know, like if I wanted to 3D print all these 4 cubes all at once. I could just export this to STL, put it in the printer, and done, basically. So, do you have any questions? Well, that means that you understood everything. That's good. Congratulations. So, yeah.
Quick question, sorry. Say you found some sort of design on the internet that is kind of similar, but you want to tweak it. Is that not recommended, or what would be the best way if you kind of have this model to work off of?
That's a good question. So, so first, it will depend on the format of the design you're going to find on the internet. So, so in most cases, you know, like when you look for 3D objects on the internet, they're going to come as STL files. Okay, and the thing with STL files is that you can, you know, they're kind of a block. You know, like it's sort of a black box, in the sense, you know, that STL files are just a set of Cartesian coordinates which actually make your object. Okay, so while everything is parametric here, in the case of an STL file, it's not going to be parametric. So in OpenScad, you can import an existing STL file in your design, you know, and I forgot what the function for this is, you know, like, but I think it's like import or include or something like that, you know, like you just like import and then the path to your STL file, and then your STL file will be rendered in here. So once it is imported in OpenScad, it's gonna be usable as a module. Okay, so if you want to put like a hole through your STL file, you're gonna be able to do it, you know. But if your STL file is a very complex object, say it's like a bunny, like with very fancy ears. So if you want to modify the shape of the ear, you're only going to be able like to do transformations which are like standard transformations, you know, like scale or whatever, you know, like, but where you're not going to be able like to reshape completely like the shape of your bunny here, you know, like just like if you had access to all these things, like if you like if you had the source basically, you know, like of your object. So you can also find people who share their OpenScad code, you know, and there's a fairly big user community. So so in that case, you can do everything you want, you know, because if you get the source of your object, then it's super easy to modify it, you know, because you have the source, you know. Like, but in the case of an STL file, it's you can modify it, but it's more complicated. So yeah. Any other questions?
David has a good question in the chat. He's asking, how about FBX and then converting to STL, or using Maya to modify a file and then save to STL somehow? Maybe David, if you wanted to ask that out loud, just in case there's any kind of clarification.
Yeah, no, that's basically it.
Yeah. That's a good question too. So so one thing that I didn't mention here is that in OpenScad you can you know, like we only looked at the paradigm where you start from a 3D object, right, and then you combine those 3D objects to create more complicated objects. In OpenScad, you can take the same approach as the one that you would take in SolidWorks. And in that case, you start from a 2D object, you know, like so a circle, a square, a polygon, and then you extrude it. And you can do like linear extrusion, you can do like a rotate extrusion, and then it's really just the same as if you were using like a more standard CAD software. So the reason why I'm saying that is because in some cases, you know, like especially if you want to create like a very complex shape in OpenScad, this approach might be better, you know. And so you want to start from a 2D complex shape, and then you extrude it, you know, and then you get the shape that you want. And so for that in OpenScad, you have the polygon object. And the polygon object allows you to create a set of points in a 2D space, so x, y, x, y, x, y, and then you basically create a path between them. So so of course that's kind of tough to do that because if you want to create a very complex shape, you will probably end up with a very, very, very long list for your polygon. And I'm not completely answering your question, David. But that's part of the answer. So that's why I'm saying all of this. But if you go then on the page of Lab 5, hello. So if you go on Lab 5, there is a section that says some tips on making the best of OpenScad. And there is a link to this super cool tool, which is Inkscape to OpenScad. Inkscape is like Illustrator. It's a vectorial graphics software to do like 2D drawings. And basically what this is just an extension that you add to Inkscape that allows you to export polygons to OpenScad. So you can export a 2D shape to OpenScad as a polygon, basically. So you can draw something in Inkscape and then export it to OpenScad as a polygon. And that's very, very useful, because it means that you can create like super complex shapes in Inkscape and then use them in OpenScad and then extrude it to get like the 3D version, and that's part of Lab 5, So if you're curious about it, like you'll actually have to play with it a little bit in Lab 5. So that's for Inkscape, but then if you wanted to use DFX or stuff like that, which usually is more like 2D, I'm not sure if you can import DFX directly to OpenScad, but DFX is a very basic and open format, so I'm pretty sure that it would be like very easy to write like a script in MATLAB, as you were mentioning, to basically generate like an OpenScad polygon from a DFX object, and because once again it's just a set of coordinates in a 2D space to create a path, and so.
Do you mean FBX? You said DFX. Do you mean FBX? I was asking about FBX.
You were asking about, sorry. So
FBX is a file format that's pretty common for animations and things like Maya or maybe Houdini even, or Unity. And it can contain animations, but it also just contains vertex information, exactly what you were saying.
Okay, sorry. I thought you said DFX. And maybe FDX is called, because DFX is like a super old standard. It already existed like probably 30 years ago. So FDX, I'm not sure. I would say if it contains animations, I would say probably not, because
But you could extract a single frame that just contains vertices and connections of the vertices.
Absolutely.
So,
yeah.
Yeah. Okay.
And I suspect that FDX is probably using DFX internally. So just a guess. So yeah. Any other questions? Cool. So before, because at the end of today's class, I just want some people to play their Lab 3 video or like homework 3, just so that we can talk a little bit about that. But before we do this, there are two things that I wanted to tell you about. So the first one is if you go on the course website, which I think I just opened here. If you go in the schedule, you won't see that we are week 5. So I'm happy to announce, I'll send a reminder about that. There is actually a bonus guest lecture by Lloyd May, who's a first-year PhD student at CCRMA. Lloyd is talking about accessibility for music makers. So if you click on the link, there's a YouTube video that Lloyd kindly made for the class. It's short, it's only 14 minutes long. So I invite you to all watch this video. It is a very trendy field in NIME, like the field of accessibility of digital musical instruments. So this is something that interests you, like the field of NIME at large. I really recommend you to, well, you should watch the video anyway, like so. Another thing that I want to say is that Lloyd has kindly accepted to hold office hours next week if you want to talk with him about this, basically, like the content of the video and just like this field in general. And so if you go on Canvas, if you look at the class schedule, you will see that, sorry, if you go in the Zoom section, you will find a link to, where is it? Discussion with Lloyd May on Monday, May 3rd at 1 p.m. for you. 10 p.m. for me. So sorry, like this is on my time zone. So basically, yeah, Monday at 1 p.m. Lloyd will hold office hours to talk about the content of this video, and I will send a reminder about that. So yeah. Questions about this, or this is just an announcement, basically. So probably not. Great. So before we watch some of this week's lab videos, I just want to say that we're reaching a point in the quarter where like you know already a fair amount, or at least, like, I'm sure some of you are a bit lost, like, and it's normal, like it always happens in this class at this point in the quarter, because it's so dense and we're doing like so many things. But I think you're probably starting to get the global picture, like like using Faust for DSP, using the TNZ for your embedded system, like the sensors, the controllers, and etc. So I think it's a good time for you to actually start thinking about a potential final project, right? So we're not really yet at the point in the quarter where we're gonna like actually start talking about final projects, but I just want to invite you to keep that somewhere in your head. This is already week 5, and this quarter is short. It's only 10 weeks. So I think it's good if, as you're doing your assignments, as you're working on your labs, you start thinking of a potential final project that you would like to do. So just putting out here, and I'm not going to talk more about this now, but just think about it. Think about like potential final projects. Final project for Music to 58 are really, really open-ended. You can do whatever you want. If you want to do something that is bigger than a car, go for it. If you want to do something very small, go for it. It can be an interface, it can be an instrument, it can be like really whatever you want. The only requirements is that it should generate sound, and it should be standalone, because we get the TNZ, and that's the advantage of having devices like the TNZ. They allow you to make like standalone objects. So basically, like anything that you did for your Lab 3 could qualify for a final project. So sensors, embedded audio, and then it can be big, it can be small, it can be really whatever you want. So the requirements are going to be like really, really for final projects. But anyway, we'll talk more about final projects another time. I just wanted like to start talking about this so that you have that somewhere in your head, as I said. So anyway, is there anyone here today who would like to share his screen to show us the video he made for his lab 3? And if no one decides to do it, I will choose someone. Okay, so please. Does someone want to show his video? Please. I don't want to force people, so it would be very nice. If someone could actually go ahead. Okay, well, I'll choose then. I didn't watch all of them, but anyway, maybe Sandesh can show his video, for example. Sandesh?
I can show a video if he doesn't want to go.
Sure. Okay. Well, Maurice, go for it. Maybe Sandesh is not completely awake.
Can you guys see this?
Yep.
And then I'm just gonna, I think you should just be able to hear my sound.
Yep.
So my setup for the
good?
music box.
Yep.
It was coming through your
It was
laptop
it was
speakers, I
working
think.
and it stopped working, like the sound. Like, did you go
That I
Oh.
back?
No.
Yep.
Did you tick the share computer sound box when you set up your share, Maurice?
Yeah. Well, let me see. Does it work
So
now?
my setup for
Yeah, it works. Yeah.
the box,
Okay.
assignment involves a sensor, and I'm using the sound bowls that will like kind of dumbed down, thinned out sound bowl so that it would upload to my Teamsy that I used in the first homework assignment. And then there's some high pitch overtoning going on. It might be because I've used a shared pen. I'll have to troubleshoot that later. But then the idea is the sensor I'm using is a galvanic skin response sensor, and I have it. Ordinarily, you want it both electrodes on your own skin, and then as you hold your breath or you are frightened, the capacitance of your skin changes. But in this case, we're putting one electrode on each of us so that when we touch, we will generate pitch at the capacitance of our total, I guess, skin capacitance. So it's going through our skin. So this is a tap, and then the more surface area, the lower the pitch. And then it's kind of cool mechanism.
So for my instrument, it's pretty much the same mechanisms as Ray's, except I'm using the code from the pentatonic soft harp as the fast example. And when we touch, it will add more voices. So put on your little finger sock.
Awesome.
And I have Sundishes pulled up, and I can play that to close this
Cool.
out, maybe.
I just want to.
Yeah, thanks.
This was super cool, Marys. Thank you. I'm just curious. This is a question related to the question that you asked me by email. You know, like, but so does Ray have a Teensy, or are you like sharing a Teensy? I'm not sure.
Or we shared a Teensy because I couldn't make sound out of my Teensy consistently. So yeah, I just loaded my code onto his Teensy.
We might have lost Romain there for a second.
I think he's just contemplating.
It's just very still.
Since there is a pause, I wanted to congratulate you, Doug, for your award. That's so cool. Congrats.
Thank you so much. I appreciate it. Yep, there he goes. Okay, we're a little bit over time, I think, at this point. So for those who want to stay around and see Sandesh's submission for assignment 3, a little bit ahead of schedule for when I'll release them later after feedback has been sent out, I can share that now. Anybody at this point who needs to go, you're of course welcome to, as always, send questions, set up meetings with us if you want to one-on-one, or come to office hours, since we have every day covered except for Thursday between the two of us. So with that, here's Sandesh's instrument.
My instrument has a laser pointer and a sharp sensor at one end and a photoresistor at the other. Interruptions on the laser beam create sound, and these are detected by the photoresistor. The sharp sensor controls the pitch of the sound by detecting the position of the hand on the laser beam. Thanks, Doug.
Yeah, that's super cool.
Um,
Starts to sound like a dying Pac-Man ghost there at one point.
Welcome to the
Yeah.
Superfast Instagram
Whoops.
Q&A. I hope you enjoy.
Yeah, well, do you want me to explain it?
Your
I saw
stance.
some questions. Hello?
Yeah.
Yeah, do you want me to explain it? I saw some questions.
Yeah, please.
Yeah.
Yeah, sorry, my Zoom just literally crashed. So
Romain, that's what happened to me like 5 minutes ago.
yeah, there we go. Yeah, so it's part of the deal. But yeah, please explain it. Yeah.
Yeah, so basically, my idea was like plucking the laser beam, like someone said in the chat. That was what I envisioned. So really it's quite simple, like has a laser beam at one end and a photoresistor at the other. The main challenge was really to aim the laser beam at the photoresistor because it's quite far away. The photoresistor basically detects the interrupts, and then the sharp sensor it detects the position of the hand on the laser beam and changes the pitch accordingly. Has a lot of flaws at this point, I think. Maybe I can work it out with Romain
I
and
don't know.
Doug.
It looks fairly controllable considering the kind of technology it's using. Actually, like I was very surprised, like to see like how well you can actually control the pitch with it. So so that's good.
Yeah, like I think the one of the biggest problems that I was facing was it's not smooth. Like let's say if I keep my hand at one point for a long time, it still like fluctuates and
Yeah. Well, you can do you know, like you can always like help that with some filtering, you know, like, but filtering will add more latency, right? So
yeah, I did put a filter, like I coded my own filter to kind of reduce uh, uh, to keep the latency up, but it didn't work.
yeah. Okay. Well, we can talk about like, because there are actually maybe solutions to this problem, you know, like, but yeah. Anyway, great work. So I think we're gonna call it for now. But yeah, for those of you who have questions, you know, I can stick around a little bit, you know, I can